So for those of you that weren't here last time, we talked about the Netflix machine learning competition, and specifically about ensemble methods for combining models into meta-models. And the topic of feature extraction came up and sparked some interest. So this time I'm going to be talking about feature extraction. So there's a few different kinds of feature extraction, or a few different problems that come up in feature extraction. And one of the types of extraction that you can do is taking variables that you have and deriving new information from those variables. So creating new columns in your data set, rather than trying to pick out the important ones from the data set you already have. So as an example, consider the case of choosing whether or not to go with somebody in their car based off how much you expect to enjoy the ride. If you plot position, let's say you have this data on hand from a previous ride with this person. You have position over time, and at some point they were driving and then they stopped. This on its own is not a decent predictor of how enjoyable a given ride is. You need to take it and transform it a little bit to get some information about the dynamism, how the situation evolves over time. So one way to do this is take the integral and turn this into velocity. So velocity over time for a plot like this might look something like this. But still, this isn't quite enough. This actually turns out not to be a great classifier of how enjoyable a ride is. And even acceleration, let's say that this is 0. Acceleration for this might look something like this if you take the integral. And again, better predictor, but still not the best. Actually, it turns out for ride enjoyment, the best predictor is the integral of acceleration, which, if you know much about physics, this is called jerk. So the quantity of jerk experienced by the person in the vehicle, it would look something like this if you take the integral of. If you take the integral of this, it should look something approximately like this. So the enjoyability of a ride is directly proportional, as it turns out, to how much of a jerk the driver is. So that's one method of extracting features, by taking the data you already have and adding new columns that describe how those columns change over time. And that's a very powerful technique, assuming, of course, that you know something about the underlying system. Sometimes you don't know how to put this data together to extract interesting information out of it. And that's actually the more common problem. A lot of things that people are working on today involve hundreds of variables, thousands of variables, and trying to figure out which of those are important is a really, really important step in analysis. And the reason behind that is fairly straightforward. Let's assume you're making a linear model of your data, trying to predict a quantity. Each individual coefficient that you estimate in that linear model will increase the amount of error that you experience. And number of coefficients. And let's say your error is here. The error that you'll experience as you increase the coefficients will increase a little bit over time, maybe approximately linear. This is really like fudge factor. You don't know necessarily how much additional error you'll experience for each additional column that you include in your analysis. But if you have anything more complicated than a linear model, the amount of error you experience starts to look a little bit more like an exponential. And that's because every additional coefficient you estimate is another source of possible error. So how do we figure out what's important in the data? How do we figure out what variables best describe what we're looking at? So one of the common techniques for extracting the important components of your data is principal component analysis. And basically, principal component analysis looks at the data as a whole and tries to capture it as much of the variance as possible in a new vector that describes your data. So I'll look at an example of wine. So I'm just going to load the data here and plot every individual variable against every other variable. So in our data set, we have alcohol, malic acid, ash. Actually, I'm not sure what ALC stands for. Alkaline ash. And then Mg is magnesium. And then we have what type of bottle of wine we're looking at. So when you're trying to extract features from a really large data set, actually, there's so many dimensions of this data, I can't actually show it on a scatter plot on my screen and still have it readable. It's actually a 14-dimensional data set. So when looking at a scatter plot like this for the first time, when just kind of getting an idea about your data, you're going to want to look for anything that looks vaguely linear, like there's some kind of relationship happening here. This one stands out to me. A lot of the others look pretty flat. Maybe this one here, and maybe this one, a couple others. But in general, you're going to want to look for variable combinations that have some kind of relationship between each other. So let's zoom in on ash and alkaline ash and see what we can see. So this will plot individual types of wine against the amount of ash contained in that wine and the alkaline ash. So you can see, can everybody see this okay? You can see that the red type of wine is kind of in the bottom right-hand corner or so, give or take a little bit. And the green sort of tends a little bit upward. Blue as well is sort of spread up and to the right. But there's still a lot of mixing going on. These two variables can't really describe what kind of wine you're looking at on their own. So what if we had another dimension, maybe out from the projector in this direction? So it's sort of 3 dimensions. Maybe we could slice green from red if green is closer to you and red is further to the screen. Or maybe we can describe a plane that goes through here that splits green and red just slightly better than looking at ash and alkaline ash on its own. We can plot, or we can compute the principal components and get a summary of those and how they describe our data, or the proportion of variance that's contained in our data. So here I've computed the principal components, and maybe I'll show you exactly how many people are not familiar with principal component analysis. Okay, so is everybody able to see this okay, or should I turn the lights on? Okay, so let's say I have 2 variables, variable 1 and variable 2. And my data is spread throughout this space, like so. The goal of principal component analysis in general is to take the amount of dimensions that you have and reduce them. Basically, for us, we want to reduce this 2-dimensional set of data to a single dimension that describes as much of the variance as we can. So the intuition behind this is basically fitting a linear model to your data. That's not exactly what happens, but you want to draw a vector that penetrates the maximum amount of variance possible. In this case, it's this line or so. If you wanted more principal components, you would iterate by taking the vector that's orthogonal to this, that consumes the next highest amount of variance, which would be about that. You can picture it describing the variance of this group as a whole, like that. So once you've conducted principal component analysis, you want to take the data and force it into the lower dimension that you've produced. So in this case, this dimension is described by this line. So you just kind of snap, you could think of it as snapping these points to this lower dimensional space, so that you're only getting this component of their information. So now all the variance is in this direction, and you can describe these points with just a single dimension rather than two, while still capturing the majority of the information involved. That's the goal. So you might think that by reducing the amount of information that you have, you'll actually reduce the predictive accuracy of your model. But what you might be doing actually is removing noise that's actually fooling the model that you're trying to build, or that's interfering with the problem, or interfering with the model building process in some way. And for each additional dimension, as I mentioned previously, you're also incurring the cost of additional error.
Is there a rule of thumb on how much you can throw away? Or maybe
so
that's not the right term,
there's a rule of thumb, but it's pretty varied. So every statistician you'll talk to has a different rule for how much variance they're willing to accept, or how much variance they want to capture with their principal components. So I know a few statisticians that would say about 70% or higher is about where they draw the line. Others will say, I want 95, which is pretty high. It's a little too conservative, I would say. But,
Sorry.
Yeah.
So PCA doesn't take into account the variable you're trying to predict.
No.
It's just reducing the variance. So
So-
when you're showing us the colors, that has no relation to how PCA functions or works. Right?
No, this is just to give you an example of how your data is stratified by dimensions that exist already in your data before doing any principal component analysis. We'll look at a spread of the classes in a lower dimensional space of the 14-dimensional one that describes wine.
Okay.
And you'll see how using principal component analysis, you can actually split these classes apart, but in a lower dimension.
And one more question. The graph before,
Yeah.
you were plotting one variable to another, right? It was like
I should have described how scatter plot matrices work. So these individual diagonal plots are all the distribution of those quantities.
Oh, okay.
And then this column is all alcohol.
Right.
And across there, that's all alcohol. And this is alcohol versus malic acid.
Right.
And likewise, this is also alcohol versus malic acid.
Right. Yeah, I was confused because of the distributions. I was thinking if it's
Okay.
when it's malic acid, why is it not like straight? But yeah,
That's what those are. And these are actually the trends.
Yeah. Yeah.
So that you can pick them out visually very quickly.
Got it.
Any other questions about this guy? Yeah.
Actually, just an interesting comment. I met with a client this week that does mass spectrometry analysis on
Cool.
wine data, and they're able to do enough PCA to nail down a wine to a particular region.
Yeah. It's a very common practice with
Yeah.
wine in particular, principal component analysis. That's why I chose this one. It's a classic example. This data set, by the way, is widely available. Just search wine and statistics. It's basically the first result. Principal components. Let's have a look at these. This summary of the principal components computed from the wine data. How they're computed is not important. Just get a statistical package, run PCA, whatever. The important part is choosing which components you want and how many you want. So this row is the proportion of variance captured by that principal component. It's how much of the variance in your original data that this component is able to describe. So to word it another way, principal component 1, an invented metric produced from your other metrics, describes 36% of the information in that data set. Principal component 2 describes 19%, etc. They're sorted from most influential to least influential. And this bottom row is the cumulative proportion, the total amount of variance described after including that principal component. So after including principal component 1, you can describe 36% of your variance. After including the second one, in addition to the first, you describe 50%, then 60, then 73, etc. So the rule of thumb, as stated, a lot of people will say 75% or higher. They'll just say, that's good, that's enough. Some other people will do a Scree Plot. So a Scree Plot is just this. So on the x-axis is the principal component included in your analysis. And on the y-axis is the amount of variance not described yet by the principal components you've included. So as you can see, after about principal component 4, if you recall 73%, we have a distinct term, a distinct change in slope. And a lot of people will choose this elbow as the cutoff point. They'll say, okay, we have a distinct change in the amount of variance we can describe, let's choose 4. So I would say an appropriate amount is anywhere between 4 and 7. I go maybe with 6 or so. But there's no like hard and fast answer to this. It's just a rule of thumb. So now that we've computed principal components, let's have a look at our data stratified by principal component 1 and principal component 2, and compare that against the earlier plot of 2 variables that did a decent job of describing individual classes in our data. So this is called a biplot, and I'll explain how exactly that works. But it's a little more detailed than our previous plot. So on the x-axis is principal component 1. The y-axis is principal component 2. The individual vectors are the components which combine together to create principal component 1. For example, hue here, this quantity of this vector influences principal component 1, etc. And you can kind of ignore those for the most part, unless you really want to dig in and see how, or see what portion of the data your principal components explain. But if you're just looking to try and understand how well they stratify the different types of wine, then just pay attention to the colors. So we have 3 colors describing our 3 different wines. And you can see that principal 1 and 2 almost, not perfectly, but almost perfectly describe our different types of wine. If we're if we're less than 0 in principal component 2, we're almost certainly green. If we're above 0, we're either red or blue, and then we can use principal component 1 to differentiate between those 2. So using only 2 dimensions, down from 14, we can accurately classify what kind of wine we're looking at, which is really quite impressive. I think it's so effective in wine, or not because, but it's well known that principal component analysis works very well for this kind of measurement about wine. So let's look at a scatter plot of our principal components. So you can see there's quite a bit of interesting activity in principal component 1 and 2. But as you get further and further down, they become more and more flat. So this is what you want to see after computing your principal components. It's indicating that they're describing your data in the order that you would expect, basically. So let's train some models. First, without using principal component analysis. So I just trained a linear discriminant analysis model that tries to predict what wine you're looking at given your 14 variables. And it's 72% accurate with a standard deviation in accuracy of about 6%, which is pretty good, but let's try with principal component analysis beforehand. Our accuracy jumps up to 98%. So throwing away an enormous quantity of our data, we have better prediction accuracy because we retain a large proportion of the information, just not the data itself. And the standard deviation of the accuracy, as you can see, has also dropped significantly. So principal component analysis doesn't always work. And it's not a technique that you can rely on blindly. You have to compare its results against not using principal component analysis, or some other technique like independent component analysis, or really any other method of manifold learning. So here's a data set about irises, the flower. And I'll just show you a scatter plot of the data. As you can see, there's many more relationships between individual variables. Sepal length, width, petal length, and petal width all have rather interesting relationships between each other. And that would tell me that principal component analysis may not work. You may actually throw away too much information by trying to reduce the dimensionality of this set of data. And you'll find that actually that is the case. If we build a model without principal component analysis, our prediction accuracy is 96% with a very small acceptable standard deviation of the model prediction accuracy. But if we use principal component analysis and throw away some of that information, or throw away some of that data and try and retain as much information as possible, our accuracy actually drops to 90%. Not a huge drop, but enough to give me pause using principal component analysis. And again, the standard deviation increases. One thing to be cautious about is that although the prediction accuracy drops when using principal component analysis, you have to be careful to use cross-validation, which I do here, to ensure that by reducing the amount of information you have in your model, you're not increasing your accuracy in data you have yet to observe. So I have one more example of feature extraction, and that has to do with data from data.gov, specifically about colleges. And I played with this data quite a bit, and it's actually a popular data set on Kaggle right now. And I think I have some good examples near the bottom. The problem in this data set is actually filling in the blanks. There's so many blanks in this data that any individual row has a missing piece of data. There is not a single complete observation in the entire data set. And the only way to fill in the blanks here is to do something like some guys on Kaggle did, and which I've extended here. Basically, collecting your data together, this is SQL, and filling in the blanks by doing some inner joins on tables that do have the metadata you're looking for, that do not vary with observation, with those that do vary with observation. Basically, since I have no way of interpolating this data, of filling in the blanks using mathematics, I have to rely on techniques basically for searching for information that doesn't vary with observation, like latitude and longitude and what college, or what class the college is, or...
Can you explain what blanks you're filling in?
So, what I mean by blanks is basically some of this data is just missing. So NA right there, not available. Some of this data in this data frame is just never been, nobody been there. And if you look at the entire set of data, actually, I don't know how to show this with. So there are 0 complete cases, basically. Every single row is false. Never code live. Don't do that. So the takeaway here is that when you're dealing with data like this, actually when you're dealing with data from the real world at all, the majority of the work is spent doing this sort of thing, filling in the blanks, joining tables together, trying to figure out where this missing information is, trying to clean it up, because statistical techniques, even machine learning techniques, by and large, rely on balanced and complete data sets. There's a few instances of machine learning algorithms which ended up making racist decisions because the data that they had was imbalanced. It wasn't balanced across race. So it's very important when you make algorithms like this that you include as much information as possible, and that you have balanced data. So I did end up doing some analysis on the college data, and I found that the average cost, your math SAT scores and your verbal SAT scores were the best predictors of your future earnings, which I thought was pretty cool. This is an Anova analysis. I did a within subjects analysis, treating college and a few other variables as error terms, basically measuring the differences within colleges. So regardless of what college you go to, your future earnings are predicted well by the average cost of your education, your ability to do mathematics, and your ability to speak well. And that's it.
I have a question.
Yes.
When we looked at the flowers, the irises, and we looked at the graphs, you saw some nice relationships, and you said, okay, this means I probably don't want to use PCA. It's kind of it smells a little bit. Could you explain why that's the case?
So the reason that I wouldn't use PCA here is there's too many relationships between variables. I don't feel like I can throw away any individual variable here and not lose information that's related to something else. So
if there's relationships between the variables,
yeah.
doesn't that mean that there's like redundancy, and the point of PCA is to reduce that redundancy?
So PCA will reduce the redundancy in your data, or collinearity in your data. But reducing the collinearity doesn't necessarily translate directly to an increase or decrease in prediction accuracy, either in or out of sample. What it will do is stabilize your model coefficients. So if you have relationships or collinearity between your data, and you build a model based off that, you might have coefficients just drop negative sometimes, or positive, or flip around, because you're trying to combine two values that are related to each other, and the relationship isn't stable. Like the coefficients that you produce to describe that relationship aren't stable, because one could be positive and negative once, and the other time you could have negative and positive. You see what I mean? No.
So can we try to use analogy somehow? For example, if I had a data set and I had length in centimeters and length in kilometers,
Yeah.
that's some sort of redundancy. I'd say
It's
there's a bit of
100% redundant.
variance there, right? So say it's not exactly, the conversion isn't 100% accurate, so there's a bit of variance.
Yeah.
PCA is good in that case because we're just wanting to describe length, and we don't really care about if it's in meters or centimeters. So PCA works there.
Right.
And there's a relationship there.
Yeah.
So can we bring some sort of analogy that says, okay, these are two relationships. I'm describing it in a more general sense, and because of that, we're losing important information.
So in the centimeters and meters example, you would have that relationship basically, right? They'd be perfectly linear.
Yeah, it should be. But I'm saying, for example, say the conversion was in.
Yes.
Say people
Well,
had
this
bad
is
money.
fine. This is illustrative enough.
Yeah.
So, if you were to build a model based off that, you'd end up having some coefficient and your length in centimeters plus some other coefficient and your length in meters. And in order to accurately describe whatever it is that you're describing, you need to combine them somehow. And it might happen that that the model just chooses this one and ignores this, sets it to really low or 0 or close to 0. Or it might be that it chooses this one and makes this really close to 0. Or it might make one of them negative and one of them positive, and it just kind of cancels each other out. So your model won't necessarily be stable. So collinearity like this doesn't necessarily reduce model accuracy, but using principal component analysis won't decrease your accuracy in this case.
Right.
In this case, some of these relationships aren't completely linear, and there's information about the flowers that you're going to be throwing away. So I'm not sure how best to describe it.
I think it's for example, the sepal length and the petal length. If
Yeah.
we did PCA and throughout the petal length,
Yeah.
then that relationship we have.
It's not linear, right?
Yeah, it's not linear and it disappears, but we want that relationship. Because,
Yeah.
well, maybe.
You do, as it turns out.
Okay.
Getting rid of it lowers your prediction accuracy. Any other questions?
I notice you said you do training based on data, and I've seen in the algorithm some methods you are using. Those methods are
Yeah.
relevant, or
Yeah. So for the flowers, I used regression trees. This is what you're referring to?
yeah.
Yeah, so in the flowers I used regression trees. And in the other set I used linear discriminant analysis. Specifically high dimensionality linear discriminant analysis. The modeling method though isn't necessarily important for the message. Basically the goal here is to show you that not all models actually like having principal components extracted. Some models actually thrive on redundancy and collinearity. That actually helps them improve their prediction accuracy. Random forests, that's one of those models. It actually is very good at taking a set of data and using redundancy to its advantage.
Because
So that's a
before
really
at
good
the
question.
wine I see you use HDDA. Yeah.
Yep. It's a method which suffers without the use of principal component analysis, without the elimination of redundancy.
Why were you using cross-validation?
I was using cross-validation to avoid overfitting. Actually, principal component analysis is another method of avoiding overfitting because you're ultimately dealing with a subset of your information, rather. And using too much of the information from the local region without ensuring that it actually has an effect on your variance, it can overfit your model. It can make your model too accurately describe the very data that you're looking at, rather than data that you haven't seen yet. Data that you haven't seen yet might have different local variances or different local properties.
Do you normally apply PCA for fine-tuning or at the beginning when you start?
I usually, so when you're looking at a brand new data set that you've never dealt with before, principal component analysis or any other method of looking for lower dimensional manifolds is a good strategy, because the human brain is excellent at 3 dimensions, maybe even 4 dimensions a little bit, and we're actually really good at picking up patterns. So if you can take a really high dimensional data set and transform it into a lower dimensional data set so that you can observe it visually, you can try and understand it visually, that's really useful because you might even be able to, using your intuition, pick out interesting relationships between data. So it's a great first step.
And does it, I don't know how to put this, but
Sure.
does it usually translate into something, I guess in English? For example, I don't think PCA works on this, but say if you, again, length and then say you have width.
Yeah.
For example, maybe you want to transform that to area or something.
Absolutely.
But
Yeah.
PCA, I don't think would do that.
No, that's
Right?
closer to that form of feature extraction.
Right, exactly. Okay, but the example, so feature extraction is like width, length, and then you transform it to area. So I can make that connection. PCA using some variable, another variable, reduce the noise. What does it become? It's some unknown
It's,
thing, or is there usually a way to explain what's happening?
So you can think of it, if you picture some points in a three-dimensional space, maybe they make a surface. Maybe they make or describe a surface.
Yeah.
What if rather than looking at them as 3D, you tilted it and looked at them flat?
Okay.
You looked at the surface, regardless of its orientation, in a two-dimensional way, so that your data is spread out like that. That's kind of what principal component analysis does,
Okay.
give or take
Gotcha.
a little bit. So,
Gotcha.
because if you're looking at the surface in this direction, it's hard to tell the difference between your points, right? They all kind of look similar. But if you tilt it and rotate your information and project it on a lower two-dimensional space, you can say, okay, this kind of makes sense now. I kind of understand a little bit more about the data that I'm looking at.
Okay.
And it's the same thing for really high-dimensional data.
Yeah.
So a popular example recently, since Google released TensorFlow, everybody's been playing around with the MNIST data, which is 738 dimensions, I think, which is crazy, right? There's no way that a human being can understand that many dimensions. Not a chance. So the guy that wrote the original paper for TensorFlow has a great paper on understanding higher dimensional data by transforming it into lower dimensions using manifold learning, which is it's not as simplistic as PCA. It's a little more advanced, but it can take huge multi-dimensional data and turn it into something that makes sense visually, which is crazy. They have examples of drawing characters with points in high dimensional space, and it will just extract that character from it, which is incredible. But that's an example, right? If you drew an S, is the classic example, in a high dimensional space with some points, it's really hard to visualize, so don't worry if you can't, because I certainly can't. But the algorithms they use can actually summarize and describe that character for you in a lower dimensional space. It's really cool.
Yeah, so that's a good way to visualize an explanation, but I don't think it answered my question.
Sorry.
But
Is
it
that
was
question
super
again?
helpful. Like the final result that PCA produces,
Yeah.
the thing, is there usually like a description that goes along with it? Like I said, the
Yeah.
width, length, and then the description there is simple, it's one word, just area. But is there usually a description that goes along that encapsulates like what is happening, like the two original or whatever original things you stuck?
So I usually thought of it like taking 3D and turning it to 2D.
Yeah,
But,
that works. But
that
I'm
would-
wondering that works. But I'm wondering if there's that
There's
connection back
another
to
physical-
your original features. Like, what does it say between those two?
So
is there,
if
in your
you-
experience, I guess, like, of course, it's your interpretation, right? But
Mhm.
is there usually find one or what's the other thing?
So this guy, are you talking about taking the principal components and turning those back into intuition about the original variables?
Yeah, kind of. Yeah, kind of.
So you can see this spread of vectors that describe the variables that you're looking at, or describe the components that you're looking at, and you can use these to understand how much hue or I don't know what flav is, phenols, magnesium, how they all translate into these principal components. So what these principal components generally mean. Principal component 1 and principal component 2 both are influenced to a certain extent by hue.
Okay.
I don't think that's exactly what you're looking for, but
Perhaps not, but I think that will help if I play around with
yeah, this is
You
called.
can't get velocity or acceleration from it because
Right.
that's like an integral, and this is just taking a portion of a
Right.
vector, right? So it's
Yeah.
not a meta feature as interesting as that.
Right.
They're just kind of partial combination of existing features. So usually there's no real interpretation of it as a physical quality,
Okay.
but you can, if you think of it as a space thing, you think of it just moving it around in a certain way.
Yeah.
Okay.
It's actually a linear. It ends up being a linear combination of these quantities. So it's not multiplying them together. It's not doing an integral or differential or anything like that. It's looking at them as a linear combination of other things.
Cool. And you coined the term meta feature. Is there a term for this as the final result? Usually that people say, or is it just like because it's not really
it's a feature.
Just PCA.
It's a
okay.
it's a feature.
It's just a feature. Okay.
Yeah.
Cool.
So your model was 96% accurate, right?
Sure.
So if you take that model and run it on unseen data or different data, what's an acceptable variance, and how do you know when that model breaks? Like what range? What range would you classify it as being broken? And not broken?
I guess it ultimately depends on the units that you're predicting and the magnitudes that you expect to see. So let's say you're trying to predict how far up in the sky a rocket will launch. A prediction error of a couple meters might be acceptable. But if you're talking about how far a ball will roll on a table, then maybe a few centimeters. It's kind of dependent. So I expect to see low variation in my model's prediction accuracy. I want that, right? Because that means that my model's generally applicable. And the accuracy that I did achieve here was with cross-validation, and the standard deviation you may have seen is also the deviation of that model. So in this case it was okay, assuming that my data set is representative of the population. But if that isn't the case, then if I try and apply this model somewhere else, I may find that its accuracy suffers quite a bit.
I'm told if you do testing on next year's batch of wine, you'll probably miss the mark greatly. Because
Really?
all the components vary, even in the same region year to year. Then the levels of acid drop.
I wonder if that's a result of different weather patterns. Or
It
different,
is, definitely.
Yeah, that's very cool. So there's no general rule, unfortunately.
Looking at this diagram here, your ash versus, you said it was alkaline ash?
Yeah.
Those shows at 90 degrees in this.
Yep.
Is that reflecting what you originally saw when you took those two individual features and they seem to give quite good information?
That's why I chose them. Yeah.
Okay. So this is showing that same thing but with a lot more richness.
Yes.
Would it mean that something like the OD and the hue, which are fairly similar magnitude, similar angle,
Mm-hmm.
that those two features are probably proxies for something common to both of them? That it's hard to distinguish these two. You can see they're both significant, but you can't easily interpret anything about them. Is that how you would read this type of diagram?
I expect you're correct. Yeah.
I'm
That's
just
how I would
guessing.
read
I
that.
don't know anything about this, so.
In general, you're right. Anything that's perpendicular or parallel with your principal components is generally going to be predictive like that. And anything, sorry, you pointed out which was the
OD and the hue, the two.
OD and hue, yes.
So left.
Both of these seem to be. You said a proxy of what?
Well, they look fairly similar to each other in magnitude and angle.
Yeah.
So is this suggesting that it's going to be hard to work out which of the two is significant, or that they might both be related to some other unmeasured variable?
They might be proxies, as you said, but I'd hesitate to conclude that from just this.
Yeah.
But they certainly seem to be correlated quite highly.
So I don't know if this answers the question that was asked earlier of how you would interpret this and relate it back to the original features.
That's definitely a way of thinking about it. I haven't really looked at them that way before, but that's certainly a way of looking at them.
I have kind of a vague question.
Sure.
This PCA, it seems like basically a transform to maintain the data, right?
To maintain the information.
Yes, but make it easier to compare. And I've seen other people use different types of transforms to map their data, and then all of a sudden, oh, look how nicely these things are classified.
Like log or
Yeah.
yeah.
So how do I know when it's reasonable or what type of transformations I need to do to make my data more easily classified?
So
Pretty big.
it's a good question. It's something that comes up a lot because every once in a while you'll see a researcher modeling something and just say, "Oh, just log the data," and not explain why. But let's look at an example. Let's say that you have some quantity. Maybe it's let's say it's salary. So you have a salary, and let's say you have some quantity like this, which is your salary, and I'm not sure what to put on X. I want to relate it to something, but pardon?
Years worked?
Years worked, sure. Years worked. I'd have a better example prepared, sorry, but so let's say you have something like this and you want to kind of draw a line like that between the two and say these guys are one group and these guys are another group. This group, you color them based off some class that you're trying to predict or understand, and you find that the red ones are sort of here, the blue ones are sort of here. Then you'd want to maybe lock this data and use that as a way to split them apart, because then you'll have some pretty low values here, and maybe like they kind of look like that a little easier to split apart.
So if it looks like it follows a trend, then just...
It's there's no like magic rule of thumb for it, unfortunately. Sometimes if you understand something particular system that you're modeling, you can kind of figure it out from physics or whatever else it is that.
So it might be domain specific.
It's definitely domain specific, and it's definitely related to the distribution you're looking at. Actually, distribution is a good way. Distribution is a good way of looking at it too. So, if you look at something and you find that its distribution isn't what you want, like maybe it's a log distribution or something, and you want to turn it into something else, then you can start transforming the values to manipulate how they're distributed to something that your model is better at handling. So maybe the assumptions that your model makes about the data aren't correct until you transform the data a little bit. But it's always tricky because then you have to go from the predictions your model makes and why, and try and understand the causality of it. And dealing with a transformed set of data when doing that is kind of tricky. So try not to transform them too much unless you have to. Fair enough. Any other questions?
So 5-minute break and then we'll continue.